Hello, everyone. Thank you so much for joining us today for our penultimate Spring into STEM session. I'm just about to hand over to Dr. Enisa Karsa, who will take away today's session. If you did have any questions, please do put them in the chat or the Q&A box, and then we'll come to them at the end of today's lecture. So without further ado, I would like to hand over to Anita to give today's presentation.
Thank you. Welcome, everyone. My name is Anita. I'm a physicist, and I'm working as a postdoc at the Department of Medical Physics and Biomedical Engineering. Today, I would like to talk about a large UCL-based study focusing on Alzheimer's disease that I was lucky enough to be able to participate in. So to give a bit of background, dementias are illnesses that affect cognitive abilities such as memory, communication skills, and even mobility and mood. The number of deaths by dementia has been steadily growing in the past decades, and today dementias are the leading cause of death in the UK and other developed countries. On top of them being debilitating and deadly diseases, the care and treatment of dementia patients also cost a lot of money, especially in severe cases. Therefore, dementia is currently a public health issue, and researching options to slow, delay, or even reverse the condition is crucially important. Alzheimer's disease is by far the most common cause of dementia. It is often characterized by, and here I have to say that you don't need to know what any of these mean exactly, but an increase in amyloid beta molecules, an increase in neurofibrillary, I can never pronounce it, so I'll just stick to NFTs. And most strikingly, there's a loss of neuronal cells or brain cells, which is what you can see here in this picture. Essentially, it means that certain brain regions get smaller in Alzheimer's patients. Scientists suspect that these processes start way before patients are currently diagnosed. So here we can see the different stages of the disease. Dementia is the final stage. Mild cognitive impairment comes before that, and there is the preclinical stage before the MCI stage. And as you can see, clinical function, so this is when the disease is diagnosed, the brown line, it happens during the dementia stage or even at late mild cognitive impairment stage. But cognitive decline, so this means that when, for example, memory problems first appear, already happens before that. So before the diagnosis even happens. And there's evidence that some of the other factors that I just listed start happening even earlier than that. So even before any symptoms appear. The idea is to look at these components in the preclinical stage to allow us to diagnose Alzheimer's disease early and maybe also identify some risk factors. That means things like if you have anxiety, maybe you are more likely to develop Alzheimer's disease. And ultimately, studying this preclinical stage could help us slow, delay, and eventually reverse the disease. So the study that I'm involved in and that I'm going to talk about in a second is following the 1946 birth cohort. These people, so these are basically people who were born around the same time in 1946. They are followed by the Medical Research Council's National Survey of Health and Development. They've been followed during their entire life, and this is the oldest birth cohort study in the entire world. They are population representative. That means that they model the population of the UK very well, and we know quite a lot about them because there were repeated waves of data collection in this birth cohort. Finally, most importantly, they during this study at the time they were around 70 years old. So many of them were likely to be in the preclinical stage of Alzheimer's disease when the study was conducted. So the INSIGHT 46 sub-study, and this is the study that I'm going to talk about finally, aims to examine people from this 1946 birth cohort. Remember, many of whom are likely to be in the preclinical stage of Alzheimer's disease. It was conducted by all of these amazing people, mainly from the UCL Dementia Research Center. So here I just wanted to make it clear that this is not my study. I was just lucky enough to be able to participate in the data processing stages, and I was allowed to present this to you. I will talk a bit more about my contribution in a second. So in this study, they examined 500 people, about 500 people, at 2 time points, 2 years apart. So this is that so that we can see how the disease progressed during these 2 years, if the subjects turn out to have had preclinical Alzheimer's disease at the time of the study. So both times they had to complete multiple questionnaires on their anxiety levels, for example. There were clinical interviews to record family history of illnesses, among other things. They underwent physical and neurological examinations. They had to do a lot of memory tests. And there was also sensory function examination, so hearing, vision, and sense of smell. And they also underwent a 60-minute PET MRI imaging session. All of these tests are essentially looking at various things that are suspected to be either risk factors or markers of the preclinical stage of Alzheimer's disease. From the title of this talk, you may already have guessed which one of these is my area of expertise. So I feel like at this time, it's also good to mention that I'm an MRI physicist. Sorry. But just so you don't go away from this talk knowing everything about MRI and nothing about PET. So in this study, participants were injected a compound called flobetapir, which I'm really not confident about the pronunciation. So this is a molecule which this big part of it likes to bound to amyloid beta. And remember that amyloid beta is increasing in Alzheimer's disease. So after the injection, this compound will accumulate in places where there's a lot of amyloid beta. And there's an additional fluorine 18, which is on this molecule, which is a radioisotope that lights up on the PET image. So the PET image tells you where the fluorine 18 is, which is where the rest of the compound is, which is where the amyloid beta is. So this is basically how PET imaging works in general. You just need to change that big part of the compound to something that would bound to whatever you're trying to image. Okay, so let's move on to MRI, finally, my area of expertise. Okay, so a quick question, which one of these you think is the MRI image? I'll give you 3 seconds to think. Okay, if your answer is all of them, congratulations, you win. So MRI is a tiny bit more complicated than other imaging modalities, which allows us to examine a bunch of different things with it, basically. So what happens here, or what happened with this study, is that every research group at UCL, which specializes in one of these amazing MRI techniques, is participating in this study, which is super cool because this gives a very rich pool of information on these people's brains. But also this is why the imaging takes an hour long. So most of that time is spent on scanning people with these various cutting edge state-of-the-art MRI sequences. Okay, so how does MRI work? Usually MRI is looking at hydrogen, which can be found in the human body in a molecule commonly known as water. Essentially, the MRI scanner can communicate with the hydrogen using electromagnetic waves, like that. So the scanner can ask a question and the hydrogen then replies. And you can program the MRI scanner to ask a bunch of different questions. But the most basic is, where are you? So this gives you this so-called structural information, which you can see on the left. This is not super high-tech yet, but it can be used to monitor changes in brain volume, for example. And remember that the loss of brain volume was one of the characteristics of Alzheimer's disease. Okay, so first exciting state-of-the-art MRI technique is diffusion MRI. So neurons, or like nerves in your brain, which are essentially the physical wires that connect different brain regions, tend to arrange into these bundles. And these bundles are surrounded by water, among other things. And these water molecules can move quite freely in the direction of the neurons. oops, sorry, I don't know why the animation is not working, but anyway, so in this direction, they can move quite freely, but their movement is restricted in the other direction. So MRI can ask the hydrogen, which direction can you move in? And this tells us how the wires are physically arranged in the brain. So we can measure something called structural connectivity, and obviously defects in this physical wiring could lead to cognitive problems. So this is why this is so important to measure in these diseases. Okay, my slides are working again. The next one is functional MRI. So when a region in the brain is active, it's working, it receives more oxygen from the body because it needs more resources to work. And this is even more indirect than the diffusion imaging one, but the MRI can ask the hydrogen, is there oxygen in the blood vessel around you, or like more oxygen than usual? And then if the answer is yes, then the area is activated. And this can give us information on something called the functional connectivity of the brain. So instead of the physical wiring, this time it's about which regions like to work together. Again, a very important aspect of cognitive abilities and studying them. Oops. Sorry. And on that note, MRI can also measure how much blood is supplied to each region. So, for example, you might see on the previous one, the functional map, that a certain part does not work. It's not activated. And this technique might tell you that it's because there's no blood flow. So this region doesn't get any blood for some reason. To measure this, we can put a little tag on the hydrogen and the water molecule in the blood. And then we can, animation is not working again. Anyway, so just imagine that it went up there. So we can wait for this molecule to reach its destination through the blood vessels. And then the MRI can ask, where did the tagged hydrogens go? And this is how you measure blood flow, essentially. Okay. So finally, MRI can measure electromagnetic tissue properties, which is my specific area of expertise. So you can think about your brain as your brain, but also as a piece of material, like anything around you, basically. So it has certain properties that every material in the world has. And one of, some of them are electromagnetic properties. So how does that work? Well, MRI is essentially a big magnet which communicates using electromagnetic waves, as we discussed. So it kind of makes sense that it would be able to ask about electromagnetic properties. But just to illustrate, imagine an island in the ocean. And if you have waves approaching the island, and my animation is probably not going to work again, but okay, let's go up there. But if you have waves approaching the island from the left side, imagine these approaching, they stay nice and regular while they are far away, but when they reach the island, they get distorted. And the same thing happens with electromagnetic waves. So while they are traveling in air, for example, they look nice and regular, there's nothing in their way, but they get distorted around objects depending on the electromagnetic properties of the object. So in this study, we measured magnetic susceptibility, which is a property that tells you how magnetic something is. In this case, it's your brain. And it can give you information on, for example, a lot of things, for example, iron content, which you can imagine if you have a lot of iron, it's more magnetic, that part of the brain. So an iron content is actually an important player in many brain diseases. So that's why this is relevant to this study. And we also measure electrical conductivity, which is about how well a material, in this case, people's brains, conduct electricity. And this gives us information on, for example, sodium levels, which sodium is necessary for activation of the nerves. So this is how this ties into this study. So as you may have guessed, MRI can ask of the hydrogen, what does the electromagnetic field look like around you? And this is how we measure these properties. Well, we would like to do that, but unfortunately, the problem is that if you ask this question, you won't get these nice images, but instead you'll get this. And it takes a lot of work to go from this original response to these nice quantitative maps. which is why I personally spent years working on this. So this is where my work or my contribution comes in. And just if you'd like to know more about the composition of healthy brains and how we measure these with MRI, please check out this talk on Monday by Dr. Patrick Brooks. I really recommend this. And finally, with that, I would like to thank everyone in the study for their hard work, and specifically Professor Jonathan Schott for allowing me to present this talk to you today. All of my colleagues who know the pain of electromagnetic tissue properties mapping as well as I do. And last but not least, I would like to thank all of you for your attention.
Fantastic. Thank you so much, Anita. And I've put the link to register for our final Spring into STEM lecture from Medical Physics and Biomedical Engineering, which is delivered by Dr. Patrick Fuchs, who's on the screen right there in front of you. That's on Monday at midday, 12 o'clock. So I've put that in the chat if anybody would like to register for that as well. So if anybody has any questions for Anita, please do put them in the chat or the Q&A box. Anita, while we're waiting for questions to come through, what's next in this study? What are the next steps that you're going on to?
So it took a while to even finalize the methods that we're using to process these images. So we're basically at the stage where we currently have a robust processing pipeline, and the next step is to apply this to all the data that was acquired through 2016 to 2019, I think, or 2020, I don't know. Yeah.
Fantastic. We've got a question in the Q&A box. Thank you for an excellent talk. It was fascinating. What is the summary of your findings in the study, particularly involving the electromagnetic tissue properties in individuals with Alzheimer's?
So yeah, so that's the kind of related to the previous question. So I was trying to focus more on explaining how, like, what are the methods that we're trying to use. For this question, we haven't really processed the data yet because it took several years just to, if we go back to this slide, just to get these high quality images. That took a lot of work. So that is going to be the next step, to apply this to the data that was acquired, and then we'll be able to see what we can see. So look forward to those research papers.
Fantastic. And then we have another question. What sorts of image processing issues do you encounter with this technique?
Mm-hmm. So the first thing that you can see, that I guess this is the most obvious, is that you have these jumps. Can you see my cursor, by the way?
Yeah,
I don't know.
Yeah, we can.
So you can see these jumps in the image that you get, which is why sort of these images are not very commonly used in a lot of settings, because these are very hard to interpret and even harder to process. So the first thing is because this is due to the fact of how the MRI scanner acquires data. You have these sort of jumps, we call them reps, and but before you do anything, you need to have an image which looks like smoother than this. These are because these are introduced by the scanner, they're not real properties. So the first step you need to do is something called phase unwrapping here. So you need to like unwrap these and make them smooth, because this is like scanner introduced artifact that you need to deal with, and you need to do a lot of like extra steps after that.
Fantastic. I'm just looking to see if there are any other questions coming through. So I can't see anything in the chat or the Q&A. So let's see. So if there aren't any other questions, oh, there is a question just popped up. Besides the struggles with processing the images, what are some other challenges that you have faced as a team?
Yeah, so the one that comes to mind is, well, basically because we are sort of connected to the study, but not quite sort of part of the study, because like all of these people who I showed you, they are conducting the study and managing everything, and they do amazing work. But because of that, we like have to do a lot of, so it's kind of difficult to manage things, to communicate with them, because they have the data and then we want to process the data, and you know, you have to do a lot of managing of these two sides to be able to you know, have the pipeline ready and then have the data ready and then bring these two together. So yeah, it's hard work.
People managing, like herding cats. Oh, there's another question here. The question is, how does one get involved in studies like these?
I think this is through networks. So I mean, we are a UCL-based group, and this is a UCL-based study. So we kind of, our group, you know, found out about this, and then I mean, obviously he needed to make a case for being part of the study, because they needed to acquire additional data for us to process. So we had to, you know, showcase that our technique that we do, so this electromagnetic properties mapping, can actually provide information that might be useful. And after that, we were let into the study. We were allowed to participate, and that's basically how it works.
So it was via the research group that you're a part of?
Oh yeah, so this is not this is not really my study. It's sort of like our group is involved with is sort of part of this this big research study. So the responsibility isn't really on my shoulders. I'm just doing the work.
Fantastic. Okay. So there aren't any other questions in the Q&A or the chat. So I'd like to say thank you so much, Anita. That was a really, really fascinating talk, and a great way to round off this week's Spring into STEM lectures. So our final lecture, as we mentioned, is taking place on Monday the 30th of May at 12 o'clock. There's a link in the chat if anybody would like to join. The title of the lecture is What Are Brains Made Of? So Patrick will go into a bit more detail on that on Monday. So thank you so much, everybody, for attending. Thank you so much, Anita, for delivering the lecture today. It was great. Thank you, everybody.
Thank you.